Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. In the name of Allah, the most gracious, the most merciful. Today, inshallah, we will finish this section and we will continue talking about the next section. There will be, inshallah, homework in this section. You have to try to check if you understand well, if you get the information you have to know, okay? Because these points will be, inshallah, helpful to you, inshallah, in your next study, inshallah, bitawfiq. Last period we talked about the gravitational force, and we said that the phenomena based on gravitational forces are various phenomena, and we will talk about, or we will choose these four only, revolving the planets about stars, like when the Earth and other planets in our solar system are revolving about the sun or orbiting the sun. And we all say that this description is not accurate description to say the Earth is rotating about sun. This is not accurate description. This is one of the approximated expressions or statements, okay? Because in fact, the Earth and the sun are rotating about a third point that's called the center of the mass. Some once say most of the center of the mass inside the sun. This is not accurate too. Sometimes it will be inside the sun, and other times it will not be inside the sun. Okay, this is not our point, but I have to say this point. Okay, well, also orbiting the planets, orbiting the moons, the satellites around the planet, okay, and the ocean tides, and we talked about the ocean tides last period. We said when the ocean waters sometimes they go towards the shores, okay, or beaches, and other times they go far from them towards inside the ocean. This phenomenon is caused by what? It's caused by the gravitational force. Gravitational force of what? The gravitational force of the moon on the water of the oceans. Well, also falling objects are considered to be cases of the gravitational force. Now we will talk about the gravitational field. If you remember, we divided or categorized the forces into two categories. Okay, we said that the forces may be at distance forces or contact forces. So that the contact forces are acting in or by touch, by contact, okay? But the at distance forces, they act as a distance. So we call them as field forces, okay? So if I ask you, the gravitational forces are called field forces. Why? Because they act at a distance, okay? For example, if I ask you, there is a plane, okay? This plane is flying in the air. It's not touching the earth now. It's not touching the surface of the earth now. Is it attracted by the gravity of the earth? Yes, it's attracted at a distance, okay? And a few minutes ago, we talked about the moon, okay? So this kind of forces is called field forces. Well, any field forces, it has something called a field. It has something called a field. Okay, so the gravitational forces have gravitational field. Okay, what's meant by the gravitational field? The gravitational field is the region around the mass where its gravitational force acts. What does it mean, mister? For example, if I ask you if there is a very, very far celestial body in the space, it's far from the Earth, is it attracted by the gravitational forces of the Earth? The answer will be no. Why, mister? Because this is out of the gravitational field of the force. Okay, but if it's inside the gravitational field of the force, if it's inside the area where the gravitational forces of the field appears or acts, okay, it will be attracted. So this is the definition of the gravitational field. Well, if we want to express any field, we use imaginary lines to show two things. Number one, the direction of the field. Number two, the strength of this field. These imaginary lines are called field lines. So now we will talk about the gravitational field lines. The gravitational field lines. They are imaginary lines that, or those show the strength uh, and the direction of the gravitational field. By the way, these lines are always directed towards the object that owns the field, or the mass that's the field owner. Why? Because it shows the direction of the force. This mass attracts the things around it by its field. So all the lines of the field, of the gravitational field of this mass, will be directed towards this mass. This is logical. Okay, well, here, this is the object. Okay, if I ask you where the direction of the field here, if I put an object here, where will it be attracted? It will be attracted towards the mass. Where? In this direction. What about here? In this direction. Here in this direction. Here in this direction, and so on. Okay, so sometimes, like in this region, we will find that the lines are close to each other, and in other places like these, the lines are not closest to each other, are not close to each other. Okay, so the crowdedness of these lines show me what? Show me the strength of the field. So the number of these lines show me the strength of the field. And the direction of these lines show me the direction of the field. Well, and it's always directed towards the mass that owns the field. Well, let's clear the drawings. Well, the magnetic field lines has two cases. Sometimes they are parallel to each other, and that requires the surface of the mass that owns the field to be flat, as you see. And other times, the lines are not parallel, and that requires the surface of the mass to be not flat, like this. Spherical curved or frequent, not smooth, not flat, any surface. Well, if the lines are parallel to each other, the field is called to be a uniform field. If the lines are not parallel to each other, the field is said to be ununiform or not uniform field. Well, Mr. Give us examples on both. The first example is the Earth. The second example is what? The Earth only. Mr. Are you kidding? Both cases are the Earth? Yes. Why? Because that depends on the frame of reference that you are talking about it. For example, if I ask you, people in their daily observation, do they observe the Earth from a space shuttle on the space? No, they observe the Earth from the Earth itself. So the surface is close to them, or in fact, they are walking on the Earth. So they see the surface of the Earth flat. Why? Because they are close. Because they are close. Sorry. But if these guys who were observing the Earth a few seconds ago have a space shuttle and try to observe the Earth from this space shuttle, far from the planet Earth in space, what will they see? They will see the Earth as a semi-spherical planet. So the lines will not be parallel. So that depends on what? That depends on the frame of reference. Close to the Earth, the field is uniform. Far from the Earth, the field is not uniform. So which is correct? Both are correct, but that depends on what? That depends on the frame of reference from where you observe the phenomenon. Well, now we finished what we want to talk about in this section. And these questions are homework, inshallah Rabbil Alameen. We will discuss them fast. Number one, what will happen to the gravitational force if both masses double? What will happen? We said the force, the gravitational force, equals G times m1 m2 divided by r squared. That means F here is up, m is up, m is up. So that means F is directly proportional to m1 and m2. Fg is directly proportional to m1 and m2. Okay, that means when m doubles, Fg will double, and when the other m double, Fg will double. So double times double. So here Fg quadruples. Increase 4 times. Well, let's use blue. Okay, here the distance between the two masses halves. If the distance between the two masses halves, so the factor here is half. But let's remember that Fg is up and r squared is down. So we will use the strategy of what? The strategy of square, then flip, square, then get the reciprocal. Memorize this like your name and understand it well. Okay, here, this is up and this is down. That means they are inversely proportional to each other. Okay, so any change here by a factor will cause change in F by. the squared reciprocal of this factor. So to find the change, number one, square. Number two, flip. Flip means get the reciprocal. So let's apply this. For example, here, if f doubles, if r, sorry, if r doubles, the factor is what? Is 2. Okay, so what will happen to the f? It will double 2, 2 squared will be 4. Then flip, it will be 1/4. So f will change by a factor of 1/4. Okay, so how can I write the answer, mister? You can write the answer like this. Here, I'm talking about this, sorry, number 3. It means fg changes by a factor 1/4. Fg changes by a factor 1/4. Okay, well, or mister, we can say decrease to 1/4. No, you can say decrease to 1/4 its value. Because if you say decrease to 1/4, I may understand that you mean 1/4 Newton, for example. This is not correct. It becomes 1/4. It becomes 1/4 of its value, okay, of its initial value. Well, okay, let's repeat it again. But now we will solve number 2 because we skipped number 2. If the distance, let's remember the relationship. Distance, Fg is up, the distance is down. So they are inversely proportional to each other, okay? And the distance is squared. So the strategy will be what? Will be square, then flip. Square, then flip. Flip means give the reciprocal, So the distance between the two masses halves. It means the factor of r is half. So square means 1/4. Flip means 4. So Fg will be multiplied times 4. So we can say the gravitational forces quadruple. Okay, and or we can say increase or increases by a factor of what? Of 4. I think it's so easy, inshallah. Well, طيب, let's talk about the question number 4. Now we have 2 changes, not 1 change. The question says both 1 and 2. 1 where the masses doubles. Masses are masses. Let's remember Fg is masses are up. So M1, M2, this is 2, and this is 2. 2 times 2 will be 4. So this will give the factor of 4. What about 2? 2, we said it gives the factor of what? Of 4 also. 2, this one. Okay, so here multiply the factors. So when more than one change happen, multiply all the factors. Those are resulting from these changes. Okay, so let's say Fg equal 4 times 4, not equal. It's so wrong if you say equal. Not equal, not equal. Let's write what? We can say Fg will increase. G increased by a factor of 16. Someone may say, Mr. Can I say it will be 16 times its initial value? Yes. Someone increase to 16 times its initial value? Yes. Someone may say, Mr. Can I say it will be 16? No, because 16 means it's 16 newtons. Okay, I hope it's clear. Well, uh, inshallah, I'll give you this one number 5 to solve it yourself. So do it yourself. Let's clear. Well, what is the SI unit of each of the following? Number 1, Newton's universal gravitation constant, G. We said that this constant, the measuring unit is Newton. I told you this is a very important point to understand, drive, and memorize this. Newton, meter squared divided by kilogram squared. If you ask me, Mr., from where we got it? Okay, from the formula. The formula says Fg equal capital G times M1 M2 divided by R squared, and we said that G, capital G, is the gravitational field, the constant. Okay, so capital G equals F times R squared divided by M1 M2. Okay, so the measuring unit will be as the following. F is measured in newtons. R squared is measured in m squared, meter squared. Uh, this is mass, and this is another mass. They are multiplied times each other. So here we have kilogram times kilogram, so we have kilogram squared. So this is the measuring unit Newton meter squared per kilogram squared. Well, let's clear the graph, the drawings. What about the gravitational field? We said that the gravitational field means the gravitational field strength, which is G. We said the measuring unit of G is Newton per kilogram. Newton per kilogram. Mister, from where we got it? From this formula. We said Fg equal mg. Mister, but G here is the free fall acceleration. No, we said G here has two names in our portion. Free fall acceleration is correct, it's not wrong, but it's also called the gravitational field strength. Okay, so here Fg equal, G equal Fg divided by m. This is measured in newtons and this is measured in kilograms, so the measuring unit will be Newton per kilogram. Okay, free fall acceleration, like any acceleration, meter per squared second. Finally, circular motion due to gravity, like motion of the moons and the satellites, or what? We said any orbiting object is in free fall, so we can say it's free fall motion. Thank you. I hope that you understood well, and Alhamdulillah Rabbil Alameen. Thank you, everyone.